Good morning all. Time for a PIC assembly language tutorial where we actually write some assembly language. So what I'm proposing to do today is write enough code to simply flash on and off one of these LEDs on the demo board. So let's flash on and off LED 1, which is up there, it's D1. And if I put the link on here, this little yellow link across to GP0, then we know that the LED is on GP0, and it's GP0 that we need to raise and lower so that that LED will flash. Now I'm going to use the PIC Kit 3 today so that we can see some of the issues that relate to this particular programmer. I'm going to put the PIC Kit 2 aside for this tutorial. So which of these techniques shall we use to flash this LED on and off? Well, let's use the first one, which is the most obvious and simple, I suppose. We turn the LED on, we wait for a period of time, we turn the LED off, and we wait for a period of time. Simple. Now, which of these assembly language instructions in the PIC Instructions set, page 70 of the datasheet, shall we use? Well, there are just so many of them. Or are there? If we go right back to the beginning of the datasheet, this is actually page 1, it says that it's a high-performance RISC CPU. Now, RISC stands for Reduced Instruction Set Computer. And it says there are only 35 instructions to learn. So actually, there aren't that many instructions. And to turn the LED on, I'm going to use this one, bit set file. Well, actually I'm not. I'm going to use this one, bit clear file, because if you remember, the LEDs are tied to VDD. So to turn them on, we actually have to put a low out on GP0. So BCF will turn the LED on, but then how do we do a delay? Well, what I'm going to do initially is just use this, no operation. The delay is very short. It's only one, what are these? Clock cycles. It's one clock cycle, which is going to be 1 microsecond. Okay, to turn the LED off, we'll use a BSF, bit set F, and another delay is simply another no-op. So let's start writing our machine code, our assembly language. So I've called my new file blinky.asm. I've got an __ config statement, which sets the internal clock to 4 megahertz, or we're using the 4 megahertz internal clock, and the watchdog timer is turned off. I've put in my BCF and a no-op, and a BSF and a no-op, and end. Is that it? No, not quite. Because for the BCF opcode and the BSF opcode, we need some operands. We need some stuff to follow that opcode so that the opcode knows what it's working on. We need a file number or name and a bit number or name. Well, bit we know because we're trying to toggle GP0. That's the least significant bit in the GPIO. So we can put bit 0 in there. For file, we need to look at the special function registers in the microcontroller. So here on page 8 is a data memory map of the PIC 12F675. Some of these are the special function registers, which are all these top ones. And then a bit further down are the general purpose registers, which we can use as general RAM. And to raise and lower the voltage level, the logic level, on output pins of the microcontroller, we need to either set or reset bits in this register, the GPIO. Now for GP0, we need to set and reset bit 0, so we can think of it as this rightmost bit. The important thing is that the GPIO register is register 5. So back to the instruction set, page 70, we want to do a BCF on file number 5, bit number 0. And similarly, a BSF on file number 5, that's the GPIO, bit number 0. That's GP0 because that's the pin that the LED is connected to. So I've modified these instructions to say BCF 5, that's register 5, that's GPIO, comma 0, that's bit 0, that's GP0, that's the pin that the LED is actually connected to. And similarly, bit set file BSF register 5 bit 0. Now you've got to be a little bit careful with these numbers. I've just typed 5 and 0, but I haven't said what number base they're in. I haven't said what radix they're in. Now it doesn't actually matter with 5 and 0 because 5 is 5 in decimal. It's also 5 in hexadecimal. 0 is the same in any number base. So is that it? Well, no, not quite, because we need to tell the assembler where this program is going to reside in program memory. So here's our flash program memory for this chip. It's 1K of memory, so it's 1024 words, and the words are 14 bits wide. And the program counter is a number that points to the position in memory that the microcontroller is currently fetching or executing. And how do we tell the assembler that we want our code to start at location 0? Well, we do this, ORG 0. ORG stands for origin. It's the origin, the position in memory where we want the assembler to assemble our code. And we want it to be in position 0 because that's the very first instruction that the microcontroller will execute when it powers up. Now we can probably actually leave this instruction, this is not an instruction, this is an assembler directive. We can probably leave this assembler directive out because the assembler will probably make the assumption that we want our code at location 0. But it's good practice to put this in, origin 0, org 0. We really ought to have it. It's not safe to assume that the assembler will put it at that location. So is that it? Is that our program? Well, not quite, because after the microcontroller has executed these 4 instructions, bit clear, no op, bit set, and no op, what does it do next? Well, actually, it'll carry on executing instructions that we haven't programmed, and the whole thing will get in a terrible tangle. So what we need to do now is tell the microcontroller to jump back to this first one so that it executes these instructions in a continuous loop. And how do we do that? Well, we use one of these control operations, one of these control opcodes, and we're going to use go to address. Now it's very simple, this instruction. It's just go to, here's the operand, it's just 101, and then this long address. Which address are we going to go to? Well, we're going to go back to the beginning, so we're probably going to go to address 0. But we don't write go to 0, we write go to a label. So what I've done is I've put a label. Here it is, it's called loop because I want this thing to loop round forever. So I put a label in front of the first instruction, the bit clear, and after the last no op, I've actually said go to loop. Now the assembler will work out that currently this bit clear is at location 0, and so when it assembles this code, it will replace go to loop with go to 0. And in terms of actual machine code, in other words, actual binary, the bits that are going to sit in the 14 bits of our program word, go to 0 would be 101 000000000. That's go to 0. So is that it? Well, no, we're not quite there yet. We're actually missing some setup stuff. We're missing quite a big chunk. And to see what we're missing, I'm actually going to go back to Arduino. So what I've done here is I've actually opened up another file and copied the code from the Arduino Blink sketch into it. Now I've called it Blink C. I've no intention of using it because it's in C and we're actually writing assembly language. But there are a lot of similarities. In the loop section here, we do a digital write the built-in LED high, then a delay, then we write it low, and then another delay. Now we've got that here with our BCF, no op, BSF, no op. And the go to, which we've had to put in, is implied here because it's in the loop function. So what are we missing? Well, we're missing this bit, setup, pin mode, output. We haven't set the PIC's I/O pins to be outputs, and the default is that they're actually inputs. Now, I don't know this for sure, but it's my guess that all microcontrollers will set their I/O pins, and this particular microcontroller has 6 I/O pins, to inputs when they first boot up. It would be very dangerous to set the I/O pins to outputs, because if you have something connected here like a machine gun, and the output comes on high or low, or whichever way you've wired your logic, you could set that machine gun running when the chip first boots up. You don't really want that. So microcontrollers boot up with their I/O pins set to inputs, and that's no good for flashing our LED. So back to the data memory map of the 12F675, and alongside GPIO, which is where you set whether the pins are high or low, is TRISIO I call it, and that's where you set whether the pins are inputs or outputs. So in the same way that we want to set the least significant bit in GPIO to go up and down to turn the LED on and off, we also need to do something with the least significant bit of TRISIO to make sure that that bit is defined as an output, not an input. Now you can see here from the datasheet, page 10, that the TRISIO bits, and there are 6 of them because there are only 6 I/O pins, all default to 1s when you have a power on reset or a brownout detect. So in other words, when the chip boots up, these TRISIO bits are high. Now it's interesting to note that the corresponding GPIO bits, here they are, GPIO bits 0 to 5, are actually undefined. So although it's guaranteed that the microcontroller will have its pins set to inputs, if you then set them to outputs, it's not guaranteed whether highs or lows are going to be on those outputs. These X's mean undefined. Now, what do those 1s in TRISIO actually mean? Well, it says here a 1 means the GPIO pin is configured as an input, sometimes called TRIState. A 0 means the GPIO pin is configured as an output. Now, the default state, of course, is that the GPIO pins are configured as inputs, but interestingly, note that the datasheet shows X's here, and I think that's actually wrong, because TRISIO would have 1s here. This register boots up with 1s in all these 6 locations to ensure that the GPIO pins are configured as inputs. I think that's wrong. And it contradicts this, which clearly states that the TRISIO bits default to 1s on power up, and this seems to imply that they default to unknowns. I don't think it's right. Right, TRISIO is file 85, so we want to do a bit clear file 85, 0, because it's bit 0 that we want to pull down to a 0 to make it an output. So here it is. Here's the assembly language statement. It's BCF, bit clear file 85, that's TRISIO, and it's bit 0 that we're trying to clear. We want to put bit 0 down to a 0. Now I've put another label in here, setup, just so it looks a little bit like the Arduino code. We don't actually need that label because nothing points to it, but it does make this a bit more readable. We've got a setup section and a loop section which executes continuously. Now, talking about readability, these numbers are starting to become a bit of a problem. 85 is TRISIO, 5 is GPIO. Wouldn't it be better if I could actually write the names in there? Well, I can. Also, I've made a glaring error here because I've put 85 in an unknown number base. That could very easily be interpreted as decimal 85, and of course it mustn't be decimal 85, it must be hexadecimal 85. So I need to type in 0x to ensure that the assembler knows that this is a hexadecimal number. Doesn't matter with these low numbers because they're the same in either number base, but this one's very important. Now, to make this program more readable, I've put in a couple of these. They're EQUs, equate assembler directives. And what this means is that the word GPIO, whenever it's seen by the assembler, it equates to hexadecimal 5. So if it sees this word down in the code, it can simply replace it by hexadecimal 5. So these 5s down here I can replace with the word GPIO. This hexadecimal 85, I can replace with the word TRISIO. So here's my much more readable assembly language code. Bit clear file in the file TRISIO, the register TRISIO. File and register are pretty much interchangeable words in PIC assembly language. Bit clear file TRISIO bit 0, and then in loop we do a bit clear file GPIO bit 0. That's the bit that the LED is on. A delay and a bit set file GPIO bit 0. So, is this going to work? Well, let's find out. Let's do project quick build Blinky. And the build succeeded. Excellent. However, we have a message. Message 302, blinky.asm. Register in operand, not in bank 0. Ensure that bank bits are correct. What does that mean? Well, it means that TRISIO register 85 is not in bank 0, it's in bank 1, and that's a problem. Why is it a problem? Well, we need to return to this. It's the instruction set to find out why it's a problem. Here's the instruction we're executing, bit clear file. We're working on file TRISIO. Now look here. We've got the opcode is 0100, so it's 0100. Then there are 3 bits to specify the bit that we want to work on, that's the comma B. Then there are 7 bits to specify the file. 7 bits to specify the file? It's not actually enough, because these file addresses run from 00 all the way down to 7F. Now, a lot of these aren't actually implemented, but 7 bits only lets us address ranges 0 to 7F. We don't actually have enough bits in the instruction, the 14-bit wide instruction, to specify files beyond address 80. So what do? Well, we have to adjust this. It's the register bank select bit in the status register, which is file 3 hexadecimal. And it's bit 5, it's called RP0, it's the register bank select bit. If it's 0, you're selecting the bank 0 registers, 00 to 7F. If it's 1, you're selecting bank 1 registers. Now, TRISIO is in these bank 1 registers, addresses 80 to FF hexadecimal. If we don't properly control this register bank select bit, we won't be talking to TRISIO, we'll be talking to GPIO. And this is probably one of the biggest hassles when you're programming PIC microcontrollers. It's remembering to select the appropriate register bank. Now, this chip only has these 2 register banks, but other chips have 4 register banks and right up to 32, I think, register banks in some of the chips. So I've had to add in a couple of additional instructions. Bit set file in the status register, it's bit 5, which sets the upper register bank. Now I can talk to TRISIO. I want to clear bit 0 to ensure that the GPIO bit 0 is an output. But then I have to clear status register bit 5. Otherwise, when I come down to this part of the code, I won't be talking to GPIO, I'll still be talking to TRISIO. It's a real pain, and you have to remember to do it whenever you talk to the special function registers. Now, while I quick build this, quick build Blinky ASM, the build succeeded. We still get that message, register an operand not in bank 0, ensure that bank bits are correct, because the assembler's not clever enough to know that we've already attended to that. But what I wanted to say is that we don't actually have to keep adding these names and equating them to numbers. We can pull in a pre-built file where all this has been done for us, and I will cover that later on. And in relation to setting bit 5 of the status register high and low to select the high bank and the low bank, there is actually another command you can use called bank cell, and I will switch to that, but I'm not going to do it at the moment. because I wanted to show how this selection process actually works at machine code, bit and register level. So is this going to work? Is that program that I've just written going to flash this LED? Now, one thing I need to say beforehand is that no-op is a very short delay. So even if it does flash this LED, it's going to be flashing at quite a high frequency. We certainly won't see it. But if we get an LED come on that's kind of at half brightness, well, we kind of know it's working. So I've built this, I've created a hex file. Now I could go to Programmer, select Programmer, come down to PIC 3, and it says PIC 3 detected, connecting to PIC 3, but this is going to fail. I'm not sure how long it's going to take to fail. Yes, it says 4 bytes expected, 0 bytes received, and that's because my PIC 3 actually has completely different firmware in it, because the process of using the programmer controls in MPLAB IDE v8.92 specifically for the PIC 3 are a bit iffy. So I'm not going to use PIC 3 within MPLAB IDE. I'm actually going to say select programmer none. The programmer controls disappear. And I'm going to bring in this thing. It's the PIC 3 standalone programmer application. Now I talked about this in part 1.2. Have a watch of that if you want to know a little bit more about this. So in the PIC 3 standalone programmer, I'm going to go to File, Import Hex. It's here, it's called Blinky Hex. Let's open that. It says hex file successfully imported. And now I'm going to program the chip by saying write. Let's see if it works. Program memory, program EE, user IDs, programming successful. Yay. Right, just one thing before we return to the actual circuit board on my desk, and that is I need to turn on power from the PIC 3 to that little demo board. It's set to 5 volts. Let's switch it on. That should now be powered up. And there it is, flashing LED. Well, not flashing visibly, but it is dim, so it's probably switching on and off at a very high speed. So is this working? Is that LED actually flashing on and off? Well, one way we can tell is with the frequency counter. So I'm going to connect the frequency counter between ground and GP0. Now what I'm going to do is actually take off that link. So we won't see the LED anymore, but we can see on the counter whether GP0 is oscillating up and down. And the answer is yes, it is. GP0 is oscillating at about 189 kilohertz. Is that right? Well, it looks about right. We've got 4 instructions in our loop. The microcontroller's running at about 4 megahertz, actually a little bit faster than that. 4 instructions which are executing at 1 megahertz, so they're about 1 microsecond each. We've got 1, 2, 3, 4, but goto is also an instruction. Now actually the goto takes 2 microseconds, so we've got 6 microseconds worth of loop here. That would be about what, 150 kilohertz, but because the clock, the master clock, is running at a little over 4 megahertz because I haven't calibrated it, yes, that would add up about right. Now, we've got a problem. We're running out of time. This video is already 20 minutes long, and I need to implement delay loops to slow down the flashing of that LED. It's not connected at the moment because it's connected to the frequency counter, but I need to slow this down so that we can see the flashing LED. But we're out of time. The client's shouting at my boss is shouting at me saying, I need a solution, I need it right now. I simply don't have enough time to write the delay loops to slow this program down so that we can see the flashing. And my software programmers, they're expensive. They charge me a lot of money. So I'm actually going to use my hardware engineers. I'm going to take a systems approach to getting this LED to flash, not a software approach. If I come back to my blinky.asm file and I change this config to 3FF7, then I'll be changing the clock from a fixed 4 megahertz internal oscillator to a resistor capacitor clock. Let's do it. 3FF7. Okay, project quick build Blinky, and it needs to be quick. Build succeeded. Let's program the chip. Okay, file, import hex. In fact, it's there in the recents list. Blinky, hex file successfully imported. Write, program memory, EE. Yes, all right, boss, I'm nearly there. Programming successful. Oh, now we got trouble. Look, the frequency counter's saying 0. But remember, the resistor capacitor oscillator doesn't work unless we have that pull-up resistor. So I need to put a link on GP5 so that the resistor capacitor oscillator actually works. Yes, it's working. That's oscillating now on the LED output at 221 kilohertz. And with the frequency counter disconnected and the LED reconnected to GP0, yes, we've got that dim LED because it's running at 220 kilohertz. How do I make this flash in the remaining few seconds before I get fired? Now, any programmers watching this are probably going to be pretty horrified at what I'm going to do. I'm going to take a tantalum capacitor. Oh, I need to take that link out actually because I've already got a link soldered on. Put it on that GP5 pin and connect it to ground. Oh yeah, look at that. Flashing LED. Boss, job done. So the software is doing exactly what we told it to do. It's turning the LED on with a bit clear. That actually lowers the value on GP0. It's then using a no-op as a delay. Now the clock is running now so slowly because of this big capacitor that the no-op is actually quite a long delay. It's then turning the LED back off by raising the voltage on GP0, and then we loop round and do the whole thing over again. Product shipped. Now, of course, you programmers out there are tearing your hair out saying, well, why didn't you build nested loops where you get the CPU to just do nothing for a really long time? Well, I will do that. I'll probably do that in a follow-up episode, an episode 2 point something, to show how those nested loops work. But for the moment, we've got a result. We've got a flashing LED. So that's it. That's LED Blinky. We've written our first assembly language program. We've controlled the GPIO. We've controlled the TRISIO to set the microcontroller pin to be an output. It defaults to being an input. We took a programming approach to create the flashing loop, but then we had to take a systems approach, in fact an electronic engineering approach, that capacitor, to finish the job in time. But that's it for this episode. Cheerio.